minus zj part, and z is traveling along the circle. So that's your r e to the theta. Okay, d theta. All right, plus in 1 over 2 pi, integral 0 to 2 pi, capital F of r e to the I theta, log d theta. Now I'm going to bring this to the right-hand side and add. But then I'm going to have f of 0 divided by that is equal to f of 0. So I'm not going to look at the log. So this is equal to n log r minus log of plus log of f0. So this is just the statement is equivalent to this. How will we actually prove this? Now, since f of z is 0 free in absolute z less than or equal to r, logarithm of f of z is well defined. Okay, so the logarithm of f of z is well defined. Therefore, this integral 1 over 2 pi of the integral from 0 to 2 pi of the logarithm of the absolute value of f of r e to the I theta d theta can be viewed as the real part, because I'm looking at the logarithm of the absolute value, is the real part of 1 over 2 pi of the integral from 0 to 2 pi of the logarithm of f of r e to the I theta d theta. That's the logarithm of the absolute value, and then you've got an imaginary value which you are discarding, which is the real part of, now this part I think of as 1 over 2 pi I of the contour integral of the logarithm of f of z, now viewed as an analytic function, dz over z. Because if I put z equal to r e to the I theta, dz is ri e to the I theta d theta, and this is r e to the I theta. That cancels, gives me an I at the top, cancels this I, and I get this. But now I can use Cauchy's theorem on this, and this is going to be the real part of the logarithm of f of 0. Right? So that gives you this part. By Cauchy's theorem. Now what about the other one? You see here what is going on is your capital R e to the I theta is moving on this large circle, and the zj are inside. So your zj, r e to the I theta minus zj, is always away from 0. Therefore, technically, you can think of this as being on one side of the circle. What do you mean by one side of the circle? I can factor the r, and then I have got e to the I theta minus zj over r. So that means I got a 1, and I got a zj over r. So I'm going to the right, which is 1. But the zj over r is never going to hit 1. So we are always on one side of the circle. So that contribution will be nothing. Only the r will come out. But the r is going to come out over every 0, and that's going to give me n log r. So that's another way. So that's another way to view that. Okay. Now, right. So observe that your 1 over 2 pi, integral 0 to 2 pi, log of the absolute value of re to the I theta minus zj, d theta, is log r, which we pull out. And then you have 1 over 2 pi, this is exactly what I said, integral 0 to 2 pi of the logarithm, the absolute value of 1 minus zj r e to the minus r zj divided by r e to the I theta. Okay, so this is just a log r. Now, why? Now this I claim is log r because your integral from 0 to 2 pi of the logarithm of the absolute value of 1 minus zj over r e to the I theta d theta is the real part of the integral from 0 to 2 pi of the logarithm of 1 minus zj over r e to the I theta d theta. Now I can do a power series expansion of this because the absolute value of zj over r e to the I theta is less than 1. And I have got n zeros, and I've got a circle which is larger. So take the largest of the zeros and divide that by r, and so these are all bounded away from 1 by that ratio. Right? So it's a question of uniform convergence in that circle, so I can interchange summation and integration. So this, by power series, is the real part of, you put integral 0 to 2 pi, and now I've got the logarithm of the minus, right? So I put a minus, and then I have got a summation zj to the n over r to the n e to the I n theta, I've got a d theta, and I think I've got an n here. So n. This is the power series for the logarithm. And I can interchange the summation and integration. And I will get outside zj over r to the power of n. We take it outside and put an n outside. And I'm just integrating 0 to 2 pi e to the minus I n theta d theta. The n is starting from 1 because it has 0 there. The only integral here which is not 0 is n equal to 0. So this integral is equal to 0. So this integral is 0, each one of them. And I'm summing, and I get log r. So I will end up with n log r. So this is all right. Now, having said this, we still have to connect it with the, what has Jensen's formula got to do with our exponent of convergence? So the next theorem. So this leads to theorem 3. Theorem 3 is that the right-hand side of Jensen's formula, which is this, so that's what theorem 3 is, it says that your logarithm of r to the n divided by absolute z1, absolute z2, absolute zn is the integral from 0 to r, little n of r, dr over r, where n of r is the number of zeros of f in absolute z less than r or less than or equal to r. It doesn't matter because if it jumps at one point, then the integral at that one point, the contribution at a single point is not going to do anything for the integral. So this is what we have. So let us quickly check this. Okay, proof. That's immediately give an exponent of this. So proof. The integral from 0 to r, n of r dr divided by r, can now be broken up as follows. These zeros have all been arranged with increasing absolute value. Therefore, we do this integral by going from 0 to absolute C1. Oh, by the way, let me write here, put absolute Z1 equal to R1, absolute Z2 equal to R2, and so on. Those are the radii. So split this integral as the integral from 0 to R1 plus the integral from 0 to R2 and so on, plus the integral from Rn to R. Break it up into n integrals. Now the integral from 0 to R1 is 0. There's nothing there, but there are no zeros. The first 0 is at C1. The integral from, I should say R1 to the integral from R1 to R2 is 1. So it's dr over r from R1 to R2 plus 2 times dr over r from R2 to R3 and so on, plus n times integral Rn to r dr over r. Now this is easy to evaluate. This is log R2 minus log R1 plus 2 times log R3 minus log R2, da da da, plus n times log R minus log Rn. So you see here, I got a minus log R1, log R2 minus 2 log R2 is a minus log R1, and so on. So you end up with n log R minus the logarithm of R1, R2, Rn. That's precisely this. So that is, okay. Finally, to get to the exponent, finish this. Now, we know what m of r is. So, this here is the integral from 0 to r, n of r dr over r. Don't worry about this. This is a finite number. You can bring this to the right-hand side. Look at the left-hand side of Jensen's formula. This is an integral over a circle. So the left-hand side of Jensen's formula, the value of the integral is no more than log mr. So the LHS of Jensen is less than or equal to log mr. All right? Now the right-hand side of Jensen's formula is what we have written this way. Forget about f of 0, that's a finite quantity. Now, observe that the integral from 0 to r, n of r dr divided by r is at least the integral from r over 2 to r, n of r dr over r. It's just a crude lower bound, but it works because this is greater than or equal to, this n is an increasing function, so this has, in this integral, the smallest value is an n of r over 2. An integral dr over r from r over 2 to r is log 2. So this part here is at least n of r over 2 log 2. This part here is no more than log mr. And therefore, we get that n of r over 2 is less than or equal to the logarithm of mr divided by log 2. which is the same as saying that n of r is less than or equal to the logarithm of m of 2r, or is capital O if you want, log 2. So let's give an equation number to this, 9. Now we are about to complete the proof of the fact that this is less than or equal to 1. So what does this say? So if m has finite order of omega, so if f has order of omega, then the logarithm of mr, if m has order omega, m of r is e to the r to the omega times 1 plus epsilon. So the logarithm of omega is no more than r to the omega plus epsilon. You can write this as omega plus epsilon if you like, if you think of omega as finite. So that is m of r, and that is an upper bound for n of r. If you put 2r here, I can put 2 there. So n of r, the number of zeros, does not grow faster than r to the omega plus epsilon, which means the nth zero will grow at least as fast as n to the power 1 over omega minus epsilon. So this is growing at least as fast as this. Hence the exponent. So this means therefore, if I take 1 over Zn and raise it to the power nu, this would be convergent if nu is greater than omega. Because if I multiply, so I've got in the bottom n to the 1 over omega minus epsilon, but in the numerator, if I put a quantity which is greater than omega, that ratio can be made greater than 1 because epsilon is arbitrarily small. So this series will be compared to 1 over n to the power 1 plus delta or something, so it converges. But this is true for every nu greater than omega. And therefore, if I take the nth, I'll get something less than or equal. It may be even true less, but definitely this is the case. So that implies that mu is less than or equal to omega. This will be used to construct the Hadamard product, and then we then get to the Hadamard product with a C function, and then we look at C prime over C and get a series representation in terms of the zeros of the C function. And that will also give you a series representation for zeta prime over zeta in terms of the zeros. Okay? So we'll get to that on Monday.